Have you experienced this Bleaway Say Friday sale? Freezes the page. The instant Taylor Swift tickets go on sale. The site crashes. Saw your MySQL queries are painfully slow, and your manager keeps pushing you to optimize behave. In nearly all of these stands one protagonist, Redis. Yet many people think of Redis as just a cache. The deeper you look, the more that framing feels rago NGI. If it were only a temporary cache, why do high traffic systems like Twitter, Discord, DUBR, and GitHub all depend on I2B? It also serves as a message queue, a real-time leaderboard, and a distributed log, or even a primary database. This article starts with a concrete business problem, and then explains from first principles how Redis actually works. The CRASENES UPOCU maintain a product service that must sustain 10,000 queries per second. You connect it to MySQL, but monitoring soon fires alerts. MySQL sustains only about 5,000 queries per second. The remaining 5,000 requests overwhelm it within minutes. This high concurrency read scenario is everywhere. Black Friday. Sub-year L tickets. Aptly launches Twitter NDS. Fund them and all. Why it is one problem: the disk-based database is too slow to keep pace with user access. First, the IDAA LOSEC hit disk access is on the order of milliseconds, memory access nanoseconds, roughly 1,000 times faster. So why not serve queries from memory in IDE? The service process you declare a global dictionary called DICT in PIT home app, in Java map, in Go, and on RDE red map in C++ on a query check. The dictionary first on a hit return directly on a misquery MySQL, and insert the results so the next lookup hits memory. Storing data inside the process using its own memory is called a local CSC head. He requests reaching MySQL now drop by an order of magnitude, and 10,000 queries per second becomes easy. But new problems appear. ESCALATONA RAM OTSEC he. First, the redundant memory for high availability. You deploy 10 service instances, each caches a full copy, so you waste 10 times the memory sec on the incons st. NSYWA price changes the 10 caches do not update simultaneously, so users may see 10 different prices. A better approach: extract the dictionary into a standalone service that all instances read and write over the network. This is a remote cache. But when many connections read and write the same data concurrently, how do you handle conflicts? TRED A and thread B modify the inventory at once, overwriting each other, and it can go negative. The simplest solution is CU, NTE, RIN2E, TIVE. Use a single thread. No matter how many connections or commands arrive, funnel them onto one thread and execute them in a queue. One thread over one copy of data means no concurrency conflicts and no context switching overhead. You now have a rudimentary remote dictionary service. FOM prototype to Redis. The prototype works but feels crude, so you enhance it step by step. The SE enhancements are what make Redis multiple data type currently. Both key and value are strings, but you constantly use richer structures. So you extend the value type str engine, an ordinary string sta first, in first out queue for message queues, and recent comment stss. Et automatically dead UPL ICA TED for mutual friends and unique visitor counts as H update a single field without fetching the whole JSO, NOBJ, ECTSO, or TED. Set a scored set inherently. A leaderboard kept sorted on insertion, so a top 10 query needs no further sorting. Memory XP IRATO MRE types mean ever-growing memory, which is scarce and expensive. The simplest fix: attach an expiration time. etexpire command lets the caller set how long data lives once expired it is removed. Phi-S alone can slow memory growth substantially. CACHEVICTI on, but if caller set no expiration, memory still feels so. Add a safeguard when memory is nearly full, evict data. By POL-IC, the classic policy is liastin-reg, NTUSD, evict what has gone longest without access. DS prevents exhaustion and keeps only hot data in memory. Persistency, if the service restarts, all in-memory data is lost and traffic crashes. MySQL persistency solves this via two mechanisms, often combine EDR that ABA snapshots periodically write the entire in-memory dataset to a file like a game. Save on restart, load it to recover most. AAP pen D on LY FLE logging. Because snapshots persist only every few minutes, recent writes can be lost. So each write command is appended verbatim to a file. On restart, replaying the log restores the .ato bound file size. Redis periodically rewrites and compacts the file. If a key was modified 100 times, only the last is kept in production. Snapshots give fast restarts, and the log minimizes loss use both. Async PIFID Pro TOCOL where T interface should the cache EXP HTTP is built on TCP, but carries heavyweight machinery headers, cookies, status codes, handshakes, which a performance-focused cache does not need. So Redis works directly over TCP with its own minimal text protocol. Set key value to write, get key to read, clear and maximally performant. While T is read is combining all of this, a high-performance remote dictionary service supporting multiple data types and eviction policies, providing persistence and communicating over a minimal TCP Pro TOC OLETS full name is RAM OTDIC TO Narwiser, where red is the name is apt in essence, a remote dictionary refined to an extreme. Why is Redis so fast? Tmem Ori versus DSKQ Erie Engine 1. MySQL row requires parsing, SQL planning, execution, traversing a B-tree index, then reading from disk. The main body NECCAV ENA top-tier NVMe SSD is on the order of micros ECO. NDS Redis is a purely in-memory data structure. Store reads bypass disk and take only nanoseconds, 3 orders of magnitude faster. The powder of data struct Uris mem Ori alone is not enough. A global dictionary in your backend would do the same. EWH. At sets Redis apart is that it natively understands data struct Uri. That traditional cache knows only strings, so updating one JSON. Unfilled means fetch, parse, modify, serialize, and write back slow, and UMPLS and TIS ELST set as H and set each come with tailored operations, letting you modify data in place. EXA in PLE, a real-time leader, BOA, RDA. Traditional database must sort millions of rows by score on every refresh, unbearably slow. WI. Sorted set a hash table plus a skip list. Underneath, inserting a score orders it immediately and a top 10 query. A direct read with no resorting GOU are moving computation from the application layer into the memory layer. Syn, GLC, ED, and IO multiplex. In the most CUNTE ring 2 point red is single-threaded. How can one thread handle 100,000 requests per second? Conceit error where multed HRE ADING loses time. WHEN threads share memory, you need locks or multi-XES. While one holds the lock, others wait, and the CPU wastes time on context switching and arbitration. Redis sidesteps this entirely. Sin CE, all data is in memory reading or writing. A value is nearly instant. The real bottleneck is the network. So Redis uses I/O multiplexing on Linux the EPO system. Call RAD her than one thread per connection. A single thread monitors thousands of connections. BGNA socket has a command, ready. Redis queues it and executes commands one at a time. Big AOC, it is single-threaded commands are inherently atomic. Two users cannot DSC RAM inventory in the same instant one completes before the next begins with no locks. Modern Redis adds background threads, but only to parse network packets. Command execution stays strictly single-threaded. The result an astonishingly fast single-threaded loop, running entirely in memory. The hit then. Try CKBH, IND, persistency, wedge and read is takes a snapshot. One thread may write 10 GB to an SSD taking several seconds. While that frees the database, it would, but Redis uses a clever trick, the fork system call, with copy on write. On fork Redis creates a child pointing to the same memory, physical memory. Is not doubled, the child writes memory to disk slowly. If the parent then receives a write, the kernel copies only that page for the parent to modify. The child is undisturbed, seeing the memory frozen as of the fork. The main thread never stalls and the snapshot persists safely, so snapshots have almost no performance impact in production. Far more DANAKC read is a highly optimized system for solving distributed architecture problems. API rate, limiting str-in plus expiration, implements a sliding window limiter. Messag EQs a list as a simple queue or str-emes for a full-featured message stream. Preventing overselling atomic operations IncRDSCR and Lua scripts ensure inventory never goes negative during a flash sale. Real time leaderboards a sorted set sorted on insertion with logarithmic query cost distry, but add-log set key value NXEX30 in one command. Geospatia tracking the built-in geo commands, publish and sub-CRIB lightweight, real-time broadcasting. Its ecosystem goes further, moving the mid-data war world into memory read as JSON and in-memory MonGod for complex JSON and queries, and UPD ATSRE this year, CHN. In-memory ELSTI CSCARG. CH4 full text search, read AG rep. HGraph database functionality. Comparable to Neo4j Redis MSR IceTime series, processing and in-memory influx. DBT her is a clear ambition here to rebuild an entire data center in memory. Sales in GTO TS red engine to where we began to withstand. High concurrence rates read is an extremely fast remote DTI SEO. Now Wi-Fi all leaderboards. Rate, lim ITRS and distributed logs. It is a versatile oral UNDE rate. Speed comes from a cohesive design. In-memory data structures, a single-threaded lock-free event, loop and background, fork-based persistence. We teach its extension modules. It can even stand in for a DAT ABA SIR EDIs makes you rethink data storage instead of rigid relational. Tables over slow disk. It offers low-level structures, optimized for memory speed, wrapped in a network interface. So the next time you launch Redis, remember you are not starting a temporary cache bucket, but one of the most elegant pieces of engineering in the modern stacky. If this helped, please like, subscribe, and comment.